Good day, everyone. Today we will be discussing resonance and its role in sound and musical instruments. But before we proceed, here are the objectives of this discussion. First is to explain the concept of resonance, forced oscillation, and standing waves in relation to organ pipes and wind instruments. Second is to differentiate between open and closed pipes in terms of their harmonic patterns and frequencies. And finally, to apply these formula for open and closed pipes to solve real life examples and show their relevance in music, nature, and daily life. So, what is resonance? Resonance is defined as the phenomenon in which an object or a system vibrates with maximum amplitude when a periodic force is applied at its natural frequency. In simpler terms, it happens when something vibrates more strongly because it is being pushed at just the right timing. So, in context of sound, resonance is very important in air columns such as those found in organ pipes and wind instruments. These air columns form standing waves, which determine the pitch and tone that we hear. The characteristics of the sound produced depends on three main factors, which is the length of the pipe of the air column. That's why here in the picture you can see at the organ, different ang sizes of pipes because diha mag-depend iyahang tone. Second is whether the pipe is open at both ends or closed at one end. So open and closed pipes will be differentiated later and will be further explained. Then third is the speed of the sound in air.
Hi there, I am Andre and I will be discussing the key concepts, laws, and the principles. And in my part, I will connect it to something we all love music! First, we have forced oscillation. This is like when you pluck a guitar string and it keeps vibrating because your fingers gave it the initial push. Or when you blow air into a flute, the air column vibrates due to your breath. And that's the external force. Now we have this thing called resonance. So this is very important in music. That is why our guitar sounds louder when you pluck the string. The wooden body resonates with the string's vibration. Or sometimes makahit og high note because we are very unaware nga atong resonate na ana di siya sa soft palate. I mean, or let's think about karaoke. If your voice matches the frequency of the mic or speaker system, you sometimes hear the loud this. Yes, that's feedback, and that's resonance in action. Then we have normal modes. So in an open pipe, like a flute on an organ pipe, you get all harmonics. 1, 2, 3, and so on. That's why flutes can play wide range of notes. In a closed pipe, like a clarinet or even when you blow across the bottle, you only get the odd harmonics. The 1, 3, 5. That's why their sound is deeper and more hollow. And you know what? Fun fact, an open pipe sounds 1 octave higher than a closed pipe of the same length. That is why, I mean, if you're a musician or if you play instruments or if you play flute or clarinet, that is why flute and clarinet they are the same size but they don't sound the same. Now, we have the laws and principles. I mean, the resonance condition says that maximum sound happens when the driving frequency equals the natural frequency. So basically, in music, it's just like hitting the right note on a violin string. But I don't play violin. So it vibrates beautifully because the bow is matching the string's natural frequency. Next, the formula. So this tells us how frequency depends on the pipe length. For an open pipe, all harmonics are possible, perfect for instruments like flute, saxophones, and trumpets. And for closed pipes, only odd harmonics appear. like in clarinet or bottle sounds. Finally, the end conditions. An open end is like the end of a flute. Air can move freely, so it's a displacement antinode or maximum vibration. And we have a closed end. It is like the bottom of a bottle. Air cannot move, so it's displacement node, no vibration. Now let's focus more on the formulas. For an open pipe, F sub n equals n times V over 2L, where n can be 1, 2, 3, and so on. So here, F sub n is the frequency of the nth harmonic, while V is the speed of sound and L is the length of the pipe. For a closed pipe, F sub n equals n times V over 4L, where n takes only odd numbers, which are 1, 3, and 5, and so on. So basically, the difference is that open pipes allow all harmonics, but closed pipes only allow odd harmonics. I think that's all for my part. Thank you very much for listening.
Now let's look at some real-life examples where resonance occur. So first, seashell sound. When we hold the seashell in our ear, we often think nga madunggan na to ang ocean, but in reality, it is the resonance of the air inside the shell, which amplifies the surrounding noise and makes it sound like waves. Second is blowing across the bottle top. When air is blown across the mouth of the bottle, the air inside resonates just like a closed pipe, producing a clear musical tone. This is the same principle used in wind instruments. Then third, musical instruments. Instruments like piano, violin, and guitar rely heavily on resonance. For example, the strings alone produce weak sounds. That's why if we play electric guitar without its amplifier, hinay iyahang maproduce nga sound. But the hollow body of the acoustic guitar resonates with the strings vibration, amplifying and enriching the tone naturally. The human ear canal. Our ear canal is about 2.5 centimeters long and functions like a closed pipe. Because of resonance, it naturally amplifies sound around 3,440 Hz, which is why the human ear is the most sensitive in this frequency range. This is also the reason we can easily detect speech sounds that fall within this range. Next is breaking glass with voice. This dramatic example shows destructive resonance. If a singer's voice exactly matches the natural frequency of a glass, the vibration builds up until the glass cannot withstand the stress and it shatters. While rare, it demonstrates the power of resonance in real life.
So this time we will be solving for an open pipe. So again, open pipe means both ends are open. So if both ends are open, pasabot ani kay ang tanan harmonics are present. So the first, second, third, and so on. So if we solve for an open pipe, always did not present ang fundamental frequency ug ang overtones. So kaning fundamental frequency is ang lowest sound nga mahimo sa pipe while ang overtones are the higher sounds nga mahimo sa pipe. So we have here our question. A tube is open at both ends and has a length of 0.60 meters. If the speed of sound in air is 343 meter per second, what is the fundamental frequency or the first harmonic produced by the tube? So we have here our given values from the question wherein the L or the length of the pipe is 0.60 meters and V, speed of the sound, is equals to 343 meter per second. So since we're finding the fundamental frequency or the first harmonic of the problem, so we are going to use this formula. So fundamental frequency is equals to the harmonic number multiplied by the V or the speed of the sound divided by 2 and then multiply it to the length of the pipe. So we just need to substitute or given sa atong formula, and then if we solve it using our calculator, the result will be 286 hertz. So that is how you solve for the open pipe. So let's now proceed to the harmonics of an open pipe. So if both ends are open, all harmonics are present. So the first, second, third harmonic is present. So if ever we are asked to solve for the first overtone or the second overtone, we just need to multiply it by the number of by the harmonic number. So for example, the one we solved earlier is serve as the first harmonic number na. So here we have the first harmonic. So if ever we need to solve for the first overtone is equivalent to the second harmonic. So 286 times 2 is equals to 572 hertz. So that is our first overtone. But if ever we are asked to solve for the second overtone, which is the third harmonic, we just need to multiply it by 3. Okay, third harmonic is equals to second overtone. So 286 times 3 is equals to 858 hertz. So as you can see here sa atong slide earlier, um 286 hertz ang atong answer for the first harmonic, while here sa ubos it is saying that the next harmonics will be 572 hertz and 858 hertz. So that is what we solve for this slide. So now let's proceed to the closed pipe. So when we talk about closed pipe, one end is closed and one end is open. So unlike the open pipe, ang open pipe is all harmonics are present. So 1, 2, 3, 4, 5, 6, and so on. But when we talk about closed pipe, only odd harmonics are present. So the 1, 3, 5, 7, and so on. So we have here our question. A pipe closed at one end produces a fundamental frequency of 220 Hz. If the speed of sound in air is 344 meter per second, what is the length of the pipe? So now we are trying to solve for the length of the pipe. So here we have our given values. So ang atong fundamental frequency or the first harmonic is 222 hertz, and atong speed of the sound or the V is 344 meter per second. So in order for us to solve for the length of the pipe, we are going to use this formula. So this formula has been derived na from the formula sa closed pipe. So here, the length of the pipe is equals to the harmonic number multiplied to the speed of the sound divided by 4 multiplied to the fundamental frequency. So we just need to again substitute our given sa ato ang formula, and there you have it. We have 0.39 meters as our answer for the length of the pipe. So if the same pipe is open at both ends, 440 hertz daw ang answer sa fundamental frequency. And I will be going to explain that the next slide. So if we talk about closed pipes, odd harmonics ang present. So the first, third, and fifth harmonic. So one end is closed, one end is open. So our first harmonic will be ato ang given earlier na 222 hertz. So that is our first harmonic. So 8 times log 1. So 220 hertz kaya pa ng answer. So since odd harmonics man ang present sa closed pipe, so diretso na ta third harmonic, which is equivalent sa first overtone. So katong first harmonic nato 220 i-times na nato 3 kay third harmonic man. So the answer will be 660 hertz. And then, if we are going to find the second overtone, ang equivalent niya is the fifth harmonic. So, 220 times 5 is equals to 1,100 hertz. So, earlier, here sa ato ang slide, nag-ingon siya nga, if ang same pipe daw is open at both ends, 440 daw ang second harmonic. But since closed pipe man ni siya, so nadiretso siya sa third. So, ngano nahimong 440 earlier is kaniingon man siya kung open daw ang duha. So, meaning, ay kung open daw ang both ends sa pipe, so meaning open pipe siya. So, all harmonics are present. So, i-times siya din nato ang 220 times 2. Kay, sa 2 man equivalent ang first overtone. So, we just need to 220 times 2 is 440 hertz. So, that is why ang nakabutan diri is 440 hertz. So, that will be for my part. And let's proceed to the next part.
Good day, everyone. Now, let me wrap up our discussion with a quick summary. First, resonance happens when an object vibrates with large amplitude at its natural frequency. So, in case of organ pipes, this is due to standing waves forming inside air columns. Now, if the pipe is open at both ends, it can produce all harmonics. But if the pipe is closed at one end, it can only produce odd harmonics. So we also see real-life applications in these principles. For examples include musical instruments, human ear canal, bottles, and even the sound you get from tapping or blowing into a glass. And to describe this mathematically, the frequency is given by the formula for an open pipe is F is equal to NV over 2L, and for a closed pipes, we have F is equal to NV over 4L. Here, N is the harmonic number, V is the speed of the sound, and L is the length of the pipe. In conclusion, the study of resonance and sound in organ pipes and wind instruments shows how physics directly influences the music and sounds we hear every day. So by understanding oscillation, standing waves, and resonance, we can explain why open and closed pipes produce different harmonic patterns and how these affect pitch. The application go beyond theory. From musical instrument to human ear canal, resonance proves its importance in both science and daily life. So ultimately, resonance isn't just a physical phenomenon, it's also a bridge between science, technology, and art, giving sounds its richness and variety. And that's the end of our report. Thank you for listening.